Welcome to another instructional video from OWL, the wise choice in fiber optic test equipment. I'm Professor Jim Powers. This video will demonstrate how to certify a multimode fiber optic link using a WaveTester optical power meter and a dual OWL series multimode light source. There are 5 main steps in the process of certifying any fiber optic link. These steps are gathering link information and accessories, checking equipment and accessories for proper operation, entering link information into the certification tester if available, and setting an optical reference, also called zeroing, taking insertion loss measurements and storing test results, and then downloading stored test results to a PC and printing a certification test report. Before beginning any fiber test, the user must gather the necessary link information and accessories required to complete the test. Link information is used to help determine how much loss is acceptable for the fiber under test, otherwise known as a link budget. Optical loss measurements are compared to the link budget to determine if the fiber is good or not, which is the same as saying pass or fail. There are 5 key parameters that apply to any fiber optic test. First is the fiber type, which will be either single mode or multimode. In the case of multimode, this could be either 62.5 or 50 micron. Next is fiber length. It is important to know how much fiber is in the link under test in order to determine how much loss is acceptable for that particular length of fiber. Some OWL testers can be used to measure the end-to-end length of the fiber automatically, including the FiberOwl4 Bolt optical power meter. Otherwise, the user can use jacket markings, installation documents, or other length measurement methods such as OTDR. For best results, avoid estimating the fiber length whenever possible. Third is number of connections. A connection is the point where 2 fiber connectors mate together, such as in a patch panel, wall plate, or mating sleeve. Fourth is the number of splices, which can be either fusion or mechanical. For the purpose of calculating a link budget, most cabling standards do not distinguish between fusion and mechanical splices. Lastly, the user must determine what wavelengths they will test at. For multimode, this is 850 and or 1300 nanometers, and for single mode, this is 1310 and or 1550 nanometers. When using a micro-OWL or fiber-OWL optical power meter, these parameters can be entered directly into the device to calculate the link budget. However, if the link budget needs to be calculated manually, this is done simply by adding together the fiber loss, connection loss, and splice loss. Fiber loss is given in dB per kilometer and varies based on the fiber type and wavelength. To calculate fiber loss, multiply the fiber length in kilometers by the fiber loss. Connection loss is the number of connections multiplied by the dB loss per connection. Splice loss is the number of splices multiplied by the dB loss per splice. Most users will follow the fiber, connection, and splice loss specified in cabling standards, such as the TIA 568. It is also helpful to determine the connector type used in the link under test, which will help determine the right reference cable configuration to use. For accessories, it is highly recommended to keep at least 3 patch cables on hand, since there are 3 reference methods: 1 jumper, 2 jumper, and 3 jumper. Mating sleeves may also be required for some link configurations. Refer to OWL's video on reference methods for more information. Finally, if testing multimode fiber, the launch cable attached to the light source will also need to be wrapped around a mandrel according to cabling standards specifications. Refer to OWL's video on mandrels for more information. As you can see here, we've gathered all the accessories and test equipment that we'll need for this test. In this case, we're using the WaveTester optical power meter and a dual OWL series multimode light source. Now, we also have 3 patch cables here. Now, the reason we have 3 is because 1 cable will stay with the WaveTester when we do our measurements, but we also need a reference cable for both of the wavelengths, since we're going to be doing a dual wavelength measurement. Now, if you're doing just 1 wavelength, you will need 1 mandrel wrapped cable, but because we're doing 2, I've taken a duplex cable and wrapped it around a single mandrel. It's a lot easier to handle 1 mandrel around a duplex cable than it is to handle 2 separate cables with 2 separate mandrels. So the first thing we need to do is power on the equipment. So in order to do that, simply press the power button on both units. So WaveTester, it's down here, it's the on-off button. And then on the dual owl, we simply press the power button. On the dual owl, you'll see that the 850 nanometer indicator LED is lit by default. So what we're going to do, just for this basic measurement, we're going to use the 850 nanometer wavelength. As you can see, we have 850 nanometers already selected here, so we don't have to switch any wavelengths. They're already set. But what we have to do next is connect in the cables and make sure that they are okay to use. Now, when we are looking at the power level through a patch cable like this, our target value is going to be around minus 20 dBm for multimode. Might be a little higher, a little close, a little lower, but it should be relatively close to minus 20, and we definitely do not want it to be any lower than minus 21. Now that is for 62.5 micron cables. You'll have different results for 50 micron. Now, as you can see here, we have a reading of minus 19.62 dBm. Okay, now this is good. We expect it this patch cable to be reading at around this power level. It's a little higher than minus 20, and it's not mandrel wrapped, so it's going to be a little bit higher than our calibration level. So what we know now is that this orange cable here is okay to use. So what we'll do is remove it from the testers, and we will set it aside because we won't need it until we start taking measurements. The next thing we need to do is to measure these reference cables. Now these are the cables we're going to be using for zeroing. And since we have the dual owl here, we might as well connect both sides of this duplex cable to the different different ports here. Okay. Now, once we have this connected, you can see we have a cable connected to 850 and one to 1300. They will correspond with the two different ends over here. So first thing is, since 850 nanometer is already selected, we find the 850 nanometer reference cable and we plug it in here. Okay, we have a reading of minus 20.17. Now this is still good because remember we are looking for a value of about minus 20 dBm. Now again, it could be a little higher, a little lower. It's a little lower in this case, but it's still okay because we have not reached our limit of minus 21 dBm. Now the nice thing about the WaveTester and the dual owl is once you've checked the equipment here, you can actually zero it out. So what we're going to do is we're going to demonstrate how to zero out at the 850 nanometer wavelength. And this is really easy to do. You simply look at this units/0 button, simply press and hold the 0 button, and you zero out your equipment. Now you can see that you're reading at 0.00. What this means is that you have zeroed out your equipment. And in this case at 850 nanometers. Now what we can do is we will check the second patch cable, second wavelength. Okay, so we connect in the 1300 wavelength, and you will notice that the reading is low. Now, what low means is that there's no measurable amount of light coming into the photodetector. And as you may guess, the reason this is because we haven't switched over to the 1300 wavelength yet. So we press the lambda button here to switch the wavelength over to 1300. And remember, we want to measure in dBm, but its meter is set to dB right now. So we use this units button until the meter is set to dBm. And we also need to switch the wavelength here because it says 850. We need to make sure it says 1300. Okay, so now you see we have a dBm value of minus 19.99. That's about as close as you can get. What this means is that this patch cable is also good for using for measurement. So what we're going to do is we're going to zero out at 1300 as well. Okay, again, 0.00. So what we've done now is we've checked our equipment. We've made sure all the patch cables are good. The equipment is measuring at its calibration level, and we have zeroed out our meter and source together. Now it is time to take readings. Once we've zeroed out our equipment, we can begin taking readings. Now, the first thing we need to do is make sure that we take the testers to opposite ends of the link. So we're going to take the light source to one side of the link, and we're going to take the power meter with its patch cable that we set aside earlier to the other side of the link. Now, at this point, it would be okay just to plug this cable into the power meter detector port here. Okay. Now, before we begin, I would like to cover a couple things that we need to really remember about reference cables, particularly with the light source here. The first thing is that you want to make sure that you do not disconnect the patch cables from your reference cables from your light source once the references have been set. If you happen to disconnect and reconnect, you're not assured of getting the same reference level again, and you will likely have to re-zero and retest. The other thing you want to remember is to not let the patch cable unwrap from the mandrel. For the same reason, you want to make sure that the reference stays intact. For some reason, if the mandrel starts unwrapping from the cable unwraps from the mandrel, then you will have to re-zero and possibly do all your measurements over again. So just remember, do not disconnect from these ports and do not unwrap from this mandrel, at least until you're done testing and you're satisfied with the results. Now, the next thing we need to do is connect into our link. And for this purpose, I have this little box here that kind of simulates a fiber link with a patch panel on either side. Now, in this case, we have a 6-port patch panel. There's 6 ports here, 6 ports there. We would need to first connect into port number 1 to take our measurement. Now, what we want to do, just to keep things organized, is we can just store at 850 nanometers first. So what we need to do is set both testers to 850 nanometers once we connect our reference cables in. Okay, now you can see that, if you see there the power meter says low here. Remember, low means that there's no measurable amount of light coming into the detector. It's because we're not on the right wavelength. So let's switch the wavelength to 850 nanometers on both units. All right, and now you see we have a reading. In this case, we have a reading of 1.36 dB of loss. Now, this negative sign indicates loss. If there's no negative sign here, what this means is that there may be some issue with the test procedure, and you might have to do some investigating. However, since we have a negative sign here, where we have a valid reading, we have 1.36 dB of loss. Now, whether this is a pass or fail remains to be seen until we download the test results into the software, but we'll do that at a later time. So now that we have a reading here, what we want to do is store the reading by pressing the save button. Now, as you can see, it says save and then a number. Down here it said 001. That means you have that's test result number 1. And now that there is stored data in the meter there, we have a floppy disk icon. So what we need to do now is we need to store the readings for the rest of the fibers. And what I'm going to do is I'm going to speed that up here now. And finally, we store a reading for fiber number 6. Now, as you can see, the fiber numbers incremented as we store the results. At this point, we have 6 readings stored in the meter. So they correspond with the 6 fibers that we've tested so far. Now, as you can see, we have tested all these fibers at 850 nanometers. Now, this is a helpful tip. It's better when you're using a WaveTester and a dual owl in particular. It's better to store all the readings at one wavelength first, and then once you have all those readings stored, then switch the wavelength. That way you only have to switch the wavelength once. You only have to switch the patch cable once. It keeps the test results organized, and it's a lot quicker of a test. So now that we've stored all our readings at 850, we'll switch over to the 1300 wavelength. But first, we need to plug into port number 1 again, because remember, we want to keep our numbers in sequence. So we're going to test in the same order. That way, on the software, the 850 reading for 850 reading for fiber number 1 will stay with the 1300 reading for fiber number 1. Okay. Now, as you can see, we're connected in, but we need to switch our wavelength, and we do that by pressing the lambda button. Okay. Now, as you can see, we have a reading for 1300 nanometers. We simply press the save button again. Now, as you can see, it said number 7. It doesn't say port number 1. This is one of the things about the WaveTester that you need to concern yourself with. It doesn't let you name the fibers as you go along. It only stores numbers sequentially. So you have to be really careful with how you store your readings. That's why it's a lot better to test at one wavelength at all fibers first, and then switch the wavelength one time. So I'm going to store all the rest of the readings here, and I'll speed that process up. And finally, we save a reading for fiber number 6 at 1300. Now, as you can see, that was reading number 12, which makes sense because we stored 6 at 850 and 6 at 1300. So what we've done is we've stored all the readings in our meter. And once we have done so, we can disconnect our equipment from a link and then take the WaveTester to a PC to download the test results. Once data has been stored in the optical power meter, test results can be downloaded to a PC to produce a certification test report. First, install the USB driver and Owl Reporter software from the supplied CD or a USB flash drive. Connect the power meter to the PC using the supplied USB cable. And then power on the power meter. Then start the Owl Reporter program. The program shortcut can be found in the Start menu. When the software has started, the screen will initially say no data loaded as shown here. Download the test results to the PC by pressing either the download menu option or the download button. While downloading, the status bar will say searching for Owl device. Specific to the WaveTester, once test results have downloaded to the PC, Owl Reporter launches a link wizard. Users will be prompted to enter link information into dialog boxes, starting with the cabling standard. Click the arrow in the drop-down menu to show a list of cabling standards, then click on the standard to select. Once the chosen standard is selected, click Next to continue. Click the drop-down arrow to show a list of fiber types, then click on the appropriate fiber type, then click Next to continue. Enter the fiber length by selecting the appropriate measurement units, then typing the length number. Click Next to continue. Enter the number of interconnections and splices for the fiber under test. A connection is simply a patch panel, wall plate, or other mating sleeve. Likewise, count the number of total splices in the link under test. Most cabling standards do not distinguish between fusion and mechanical splices. Click the New Organization button, then enter the organization name and telephone number. Once the organization name appears in the drop-down box, click Next to continue. Enter the date of test. By default, the current date is displayed. However, if the date of test is different, use the drop-down menu to change the date. Finally, enter a descriptive name for the link under test. Once the test results have successfully been downloaded, the data will appear in the Owl Reporter screen. The test results can be viewed in two different formats. This view is called Circuit Detail View. It shows detailed information about a single fiber run. The other view is called Circuit Summary View. Circuit Summary View shows basic information about a group of related fiber runs. Certain buttons become active when Summary View is selected. Pass-Fail, Overhead, which shows how close the test is to its fail point, or Optical Loss. Toggle between Summary and Detail View by pressing this arrow button. Test results can be printed from the File menu or Printer button. The printout will show test results based on the currently selected view. The reports are formatted to look like the OWL Reporter screen. This has been another instructional video from OWL, the wise choice in fiber optic test equipment. For more information about additional instructional videos, or OWL fiber optic test equipment in general, please visit OWL's website at owl-inc.com. I'm Professor Jim Powers. Thanks for watching.